Okay, what we will do today. Today we will discuss what we call the dual theory. We are still in the same problem setting as in chapter 1. We have a decision maker who is facing two risks, X and Y, and he or she has to decide which one is more preferable. And we assume that X and Y are loss random variables, meaning that you will suffer the loss X, you will suffer the loss Y. So we subtract X, we subtract Y from your wallet, and which of these two do you prefer? That is the choice and the problem. And in chapter 1, we considered expected utility theory. And what was the motivation of expected utility theory? It was the following. So assume that this is our decision maker, and we have two risks, risk X and risk Y. And you have to decide which of these two do you prefer. Do you take risk X? Do you take risk Y? For example, am I going to there is a question here about the exam session. Okay, so coming back on my first point, so about the exam, at the moment, the exam is as it is announced on Toledo, right? So it means it's an in-person exam, pen, paper, you can bring your slides, handouts, exercises, everything is available on Toledo you can bring, and you can bring a calculator, right? However, I don't know, of course, what will happen in January. They may change it to an online exam. In that case, you will hear that via Toledo. But at the moment, it's as it is announced on Toledo. But you don't know. It's very hard to predict what will happen, right? And if you need to, we will change to an online exam. But if you do an online exam, the setting of the exam will be slightly changed, right? The current exam that I have is, I cannot directly translate it to an online exam. I need to make some changes, all right? So at the moment, we do it as is announced on Toledo, unless something comes in our way and we have to change that, all right? So keep an eye on the official news channels of the KU Leuven and on the Toledo website. Okay? Okay, back to our problem. We have our decision maker, and he or she has to pick X, Y. And what was I saying? Let me think. Assume that you have the expected loss, expectation of X, and expectation of Y. Now I know. So for example, your X can be if I take insurance for my car, or Y can be the situation where I do not take insurance. That would be a decision problem. Or you have maybe two possible types of insurance, right? You have insurance company 1 that offers you a certain insurance, and company 2 that offers you a certain insurance is different. So the loss that you will have after you take the insurance X, Y is different, and which one is the best to take, right? That's the type of problems we are looking at. Assume that you know the expected loss X, expected loss Y. Then one naive approach could be to only look at the expectations. Say, well, I will take what's best for me is the loss with the lowest expectation. Right? If you have to pick a loss that has an expectation of 1,000, another loss that has an expectation of 100, you go for the 100. Right? That's that would be the naive approach, because we showed with this in Petersburg paradox that your expectations do not tell you everything. We had this example with a coin tossing, right? It is in Petersburg paradox where you have a coin tossing game where you can win an infinite amount on average, and yet it's not a very good game for you, right? Although your expected loss is very high, or expected gain is very high in that case, how you look at the game is very different. right? So the expectations do not reveal everything you need to understand your gains and your losses. And for example, assume that you have a loss, x, that you have losses x and y, where expected loss x is equal to the expected loss of y. Right? Assume that you have to pick losses x and y, but they are the same in expectation. So the expectation does not reveal any difference between the two losses. Then you could say, well, if I only base my decision on expectations, the two losses are the same. I'm indifferent being exposed to x and exposed to y. However, assume that x is a certain loss. For sure, you lose 100 euros. And y is a loss where you can gain a bit and you can lose a bit. But on average, you get 100. Right? Then, of course, x is probably better than y. You prefer the certainty of knowing exactly what you have over the uncertainty that, well, maybe you gain, that would be good, but maybe you lose even more than the 100 you lose in the x situation. Right? So if you have a distribution, of course, the mean expectation of x reveals something, actually a lot about your distribution, but the tails are important. We want to take into account the tails. How is the probability mass distributed around that mean? Is it squeezed, very compact around the mean? We like that. That makes your risk more deterministic. Or is it spread out to the positive to the negative side? We don't like that. That gives you uncertainty, right? So in the expected utility theory, we found a way to deal with these tails by applying concave or convex functions on our random variable x. So we transform our losses x in the real world. So here are losses in your, say, euro world. And we said, well, actually, we are not looking directly to euro amounts. We transform that. We travel to a new world, which is the utility world. Right? So we travel from the euro world to the utility world, and instead of comparing expected losses in the euro world, we first transform everything to utility levels, and we are not comparing euro or dollar amounts, we are comparing utility levels. We are doing our comparison in the utility world. That was the idea, the motivation of chapter 1. The advantage of this approach was that this transformation with a function u from euro amounts to utility amounts gives you a way to include preferences of your decision maker. Right? You can model someone who is very risk averse. He is using a certain way to travel from the euro world to the utility world. You can model someone who is very risk loving. He has another way to transform the wealth levels. Right? So we have our risks x and y, which have a distribution, tells you how risky is my position, and we have the preferences of the decision makers. Right? And we combine these two with a, for example, expect utility, that is chapter 1. Okay? What could be a problem with these utilities? If you think about it, utilities give you the moral value, how happy you are with a certain amount, right? If you have $1,000 today, but you lose some money and you end up with 500, your utility will go down. You are less happy because you lost $500. And if you gain money, if you gain 500 euros or dollars, you will be more happy, right? And the concavity of this utility function tells you something on how is your utility increasing, decreasing in function of gaining or losing money, right? That's what we know about what we learned in chapter 1. Assume now that you will lose a lot of money, right? Assume that we are looking at what is your utility after you lose 1 million euros. And Of course, it depends on how much money you have, but at least for me, 1 million, that's a lot, right? That's far in a negative region. And if I think what would be, how happy will I be when I lose 1 million? Well, there's not a lot of happiness left over, right? My happiness will be very low. But if you compare it with losing, say, not 1 million, but 5 million, very difficult to compare what is your happiness when you lose 1 million or 5 million or 3 million or 10 million. I mean, it's just extremely low, right? So this idea of utility, it works well as long as you are in a, say, reasonable range, right? If you have a deficit of saying up to 10,000 euros and you have gains up to 500,000 euros, reasonable range that you can understand your utility function. But if you go beyond that range, it's very hard to define your utility, right? Either it's basically minus infinity if you are in the very negative side. When you have like very extreme levels of wealth, probably your utility function will behave in a very weird way, right? If you already have 10 million euros and you gain another 100,000, well, how do you define utility in that side, right? So your utilities, we can understand that as long as numbers are reasonable, but in the extremes, very hard to understand. The problem is, of course, I mean, you could say from an economical point of view, well, if I try to model my behavior of your behavior, that's fine. I can reasonably assume that wealth levels stay in that reasonable range. I can assume that you will not gain or lose 1 million euros by the end of next year. However, if you talk about risk management, these extreme cases, that's the one that we want to investigate, right? If your company has like a few percentage gains compared to last year, or they lose a bit more, that's fine, right? We do risk management to understand what can happen, for example, this year, when many businesses have huge losses because they have unforeseen closures for a very long time, and other businesses have huge gains because they basically take over all the businesses of everything that is closed due to COVID-19. Right? We are in these extreme situations. That's why we set up our risk management framework. Right? If you do portfolio management, for example, you don't need risk management for your portfolio just for a few percentage gain or losses. Right? If you by the end of this month, you see in 2020 my portfolio gained 5 to 10%, or maybe lost 5 to 10%. Too bad for you, but that's fine. That's normal, right? We can deal with that as long as you didn't bet very important money that you really need straight away. That's fine. You will recover from that if you make some reasonable adjustments. We do risk management for your portfolio to look into situations where you will lose 50% of your wealth, or suddenly you will increase by 100%. That's why we need the risk management. These are the unbearable situations. That's where we need a cushion, where we need to understand, okay, how bad is bad, right? So what I try to say here is that utility theory has its deficiencies. Well, when we talk about extreme large losses, extreme large gains, one problem. And secondly, if you do risk management, we are mainly looking in these situations, right? So that's why we say, well, maybe we should look into other possibilities, other opportunities to model these decision-making problems. And if we go back to our utility setting, we had, what should I do? Maybe do it like this. We had in our utility theory, in our expected utility theory, we use a utility function to model the preferences of the decision maker, right? And we use what should I call that? We make decisions based on what we call the expected utility. Comparing expected utilities. Right? That's what we do in the expect utility framework. The problem is that if we transform our wealth levels to the utility worlds, that kind of blurs the interpretation a bit. So actually what we understand, especially if we are working in a financial, in a actuarial setting, we understand euros and dollars. We understand the difference between a loss of $500,000 and a gain of $500,000. We all agree on that. We understand that 1 million is bad, a loss of 1 million is bad, and 10 million is 10 times worse than the 1 million, for example, right? So we can understand these very big amounts if we talk about the euro or dollar amounts. It's just that it becomes a bit not so clear how we should understand the utility attached to that. Right? So that's why we say, well, maybe we shouldn't do this conversion from euro world to utility world. Maybe we should stay in the euro world. That's the world that we understand. That's where everything happens, right? And that's the idea of what we call the dual theory. In the dual theory, we say, well, we want to talk about euros. We don't want to compare utility levels, because what is utility anyway? We want to compare euros. So what we do in the dual theory, we say, well, in order to capture the preferences, we use what we call a distortion function. And a utility function is transforming the wealth levels. A distortion function, because we don't want to transform any wealth levels. If you think about the problem, we're looking at expected values of something. If you talk about expectations, you talk about outcomes, you talk about probabilities, right? In the utility framework, we change the outcomes. Now we say, well, we don't want to do that. We don't want to change the outcomes. We want to keep the outcomes in the euro dollar world. Well, if you don't want to change the outcomes, we have to change the probabilities, right? There are only two components there in your expectation. You don't want to change the outcomes. We change the probabilities. That's what we do with the distortion function. We distort the probabilities. We keep the outcomes the same. And then we take not an expect utility, but we take what we call a distorted expectation, which is, as the name says it, it's an expectation. It's like an expected loss. The only thing what we did is we are changing the probabilities. So for example, assume that you have a game where you can gain 100, maybe I should, yeah, okay, I do it like this, and you can lose 100 with probability 1/2. Then the expected loss is 0, right? But what we say is, well, actually, if I'm looking at that game, then I attach, so 100 is a loss, minus 100 is a gain, right? I'm more concerned about the loss of 100 than I am about the gain of 100. Right? So my loss random variable can take 100. I have to pay 100, can be minus 100. I receive 100. But actually, although in reality the probabilities are 1 over 2, 1 over 2, what I say is actually I want to distort these probabilities to P and 1 minus P, where P is larger than 1 over 2, and then 1 minus P is smaller than 1 over 2. So I put more probability mass with the loss and less probability mass with the gain, making my expectation using these P probabilities, I make that expectation positive. Yeah, I push it a bit more to the positive side to build in my expectation that I'm more afraid of the losses than about the gains. Everyone understands what I'm saying here? Because that in a nutshell is what we will now try to put in a more formal framework. All right. What is important is to see that basically what we do with a distorted expectation is we take a regular expectation, but we change the probability measure. Right? That's what we try to do. And in this changing of the probability measure, that's where I put the preferences of my decision makers. Okay. So I set this. Whoops. Yeah, and I'm here. Okay. Are there questions so far? No, everything is clear. Okay. This idea of distortion, distort expectation is, and that's how we will use it in the next chapter, can be used to define risk measures, right? Because what we do in this course, we first try to talk about what is risk, and especially how is dependency related to your risk when you have a portfolio of risks. That's what we have almost done until after this lecture. And then the next question is, how can we measure that risk? How can we define a good function that tells me, well, your risk today is average and next year you do it again and then it's elevated and after that it's very high, something like that. We want to quantify the risk through a risk measure, right? And these distorted expectations give you a way to design risk measures. Why? Because with this distortion function, by changing these probabilities, what you do is you do a kind of, you put stress on your bad scenarios. You say to your insurance company is calculating the expected loss, right? What do you expect to pay in the future? You use data and machine learning to build your model and so on and so on. But then the regulator comes and says, well, can you stress the probability that things are bad? Right? Can you just increase these probabilities a bit? Because, well, we know that that you can be wrong. Maybe your data you use is a bit too optimistic about what happens in the future. It doesn't include all the information about the slowdown of the economy in the next year and so on. So let's make things a bit worse than they are in your model, right? And that you can easily do with these distortion functions, right? You can swap some probability mass from your good scenarios to your bad scenarios, right? So by applying this stress on the different scenarios in the future, you can design what they call a risk measure, which can then be used to build economic capital, right? A cushion to absorb unexpected losses. So that's what I say in this bullet point. From a mathematical point of view, the distorted expectations, we want to see it as expectations. We want to say, well, actually, I know my expected value operator, right? And the expected value is a function that you apply on a random variable, right? There's a question here. Would it make sense to apply this approach into worst risk scenarios, or they are both different approaches to consider, but no. Yeah, so the distortion functions help you to stress your probabilities, right? And depending, we will see that using different distortion functions, you can make that stress larger or smaller, right? If I go to my example here, of course, you can say, well, if I take P larger than 1/2, I stress my losses, right? I put more emphasis on my losses than on my gains. Of course, the larger you take P, the worse your stress is, right? So you can think, well, what is an adequate value for P here? Well, that's, you have different distortion functions. We will discuss that later on. If I go to worst case risk measurement like we did with the dependencies, of course, that you want to combine a bit, because you want to say, well, what was bad when we talked about dependencies is when all things are moving together, right? That was the bad situation. The best situation is when you have countermodernicity of mutual exclusivity, when things are compensating each other perfectly. And of course, you can say, well, let's apply my distortion risk measure, my distort expectation, on my combinatonic or mutually exclusive setting. Well, that would give you the worst case scenario, and then you apply you measure your economic capital, or you take the best case, right? That's and we will discuss that at the end of this chapter, and also next week we look at what are risk measures, how can we define different risk measures, and then see how do these risk measures behave when we have combinatonic risks. Okay. Okay, so if you think about your course on probability, you learned about the expected value. You have random variables, and then you can take an expectation. Right? Each random variable has an expectation. Right? It's a functional. But we can say, well, let's define a larger set, right? Such that the expectation is a member of that set. And we call this set the sublinear expectations, because with the expectation you have that x plus y is equal to the expectation of x plus y is expectation of x plus expectation of y. If you want that, there's only one functional you can define, is the expectation. However, we can say, well, maybe we change this to smaller or equal. Let's have a look at that. Sublinear expectations. You can also define sublinear expectation that are larger. But then there are more possibilities to define your operator, right? And your distort expectations are in that sense, right? And that's where the name comes from. We are still talking about expectations, but is a generalization of your set of expectations. Yeah. We are not going to dig too much into the mathematical details, but I think it's important to know that there is like a whole mathematical theory of sublinear expectations that can help you to understand these distorted expectations. Right? They are more or less the same class. Another interesting application, again, I don't have too much time to talk about this in this course, but it's developed by Dilip Madan from University of Maryland and Wim Schoutens, professor at the KU Leuven, but then in the math department, which use these distorted expectations to price derivatives, call options, right? You maybe took a course on Black-Scholes to price a call option, but then you find a single price of a call option, right? You have the Black-Scholes formula, you type everything in, it tells you the call option is priced today at 1.4. However, if you then do Yahoo Finance or you have a data set with call option price, you will see two prices. That's a bid and an ask, right? So it means that you study a whole semester on pricing Black-Scholes, and the first thing that you see in the data does not match your model. Your model says there's one price, the data says no, there are two prices, meaning your model is wrong, right? You can change the data, that's what you normally do. You just take the mean of the bid and you say, now I have again one price and we can continue. If you say, well, I want to develop a theory that does not give me one price for the call, but two, then you can use what they call conic finance. And conic finance is based on these distorted expectations. So if you understand everything what we do in this chapter, you read the book of Madan and Schoutens on applied conic finance, you will recognize the formulas, right? You will, it uses the same theory in a very different setting, okay? What I try to tell you here is that it helps to spend some time studying these distorted expectations because they are used in many fields of finance and insurance. Okay, let me first try to motivate a bit why we need a new theory next to the expected utility theory. So assume that you have two risks, X and Y. And X is deterministic and Y can take value 0 or 1, and with a small probability, only 10%, you get an outcome of 5. Assume that X and Y are income, right? You receive 0, you receive 1, you receive 5. If you compare X and Y, you see that actually they are more or less the same in the sense that it's most likely that you get 1. X is for sure you get 1. Y, it's very likely that you get 1. You have a 90% probability of getting something that is the same or smaller than X. There's only a 10% probability that you are better off with Y than with X. Right? So I don't know, you can think for yourself what would you prefer, X or Y, but it's very reasonable to assume that there are decision makers that prefer X over Y. That will go for the certainty. Okay? I don't say that everyone will go for X compared to Y. Maybe some of you want to gamble a bit, you go for Y, that's fine. But I hope that we all agree that there exist decision makers that prefer X. Okay, let's have a look at two other risks, V and W. And if you compare the outcomes, they both can have 0 with a high probability. V get 1 in the other scenario and W get 5 in the other scenario. If you compare V and W, then if you have to make a decision, that 1% difference in V and W, you cannot really feel that, right? If you gamble, that 1% will not make a difference, right? So we can safely assume that everyone will go for W here. The W is a better choice, right? Because the probabilities are basically the same. And if things are good, at least you get 5 compared to 1. Okay? Everyone agrees so far? Or some of you say, no, I think I will prefer V over W. No? Okay, so what we get is that W is better than V. Yeah? We prefer W over V. And assume that everyone agrees on that. Right? Just because, well, no one can feel that 1%. Right? It's just a very, very tiny difference. Assume that I have a decision maker that prefers X over Y. Again, I'm not saying here that everyone prefers X over Y. I say there is someone who prefers X over Y. And there's someone has a utility function, I don't know what utility function, but has a utility function such that the utility of X is larger than the expected utility of Y. Okay? So we pick someone and he or she prefers X over Y. Then the utility of X, well, X is deterministic, is just U1. The expected utility of Y, it's 0.01 U0 plus 0.89 U1 plus 0.1 U5. Right? I just take utilities times probabilities. Okay, let's write U1 as 0.89 U1 plus 0.11 U1. Right? And this is equal to 0.01 U0 plus 0.89 U1 plus 0.1 U5. Then you see you have this term here that will cancel. Right? So we end up with a 0.11 U1 is bigger than 0.01 U0 plus 0.1 U5. Okay. If you look at the risk V, you see that it has an 11% of getting 1, right? So this will account for that part of your expected utility of V. What I need to add is 0.89 U0. Right? If I add this term here, then this part here will be the expected utility of V. Right? No? So I have, well, I go back. Oops, all the way back. I have this part here. And if I, well, maybe let me have a look at V. The expected utility of V is equal to, it has an 89% of having 0, so it's 0.89 U0. It has an 11% probability of having U1, so 0.11 U1. I have already this term here. To have on that left hand side, to have expected utility of V, what do I need to add? I need to add this part here that I plug in there. So I say 0.89 U0 plus 0.11 U1. All right, so now this thing here is expectation UV, right? I added that 89% U1 on the left-hand side. I have to also add it to the right-hand side, but I already have the 0.01, so that becomes 0.9 U0 plus, you have 1, plus 0.1 U1. Correct? And then you see that at the right-hand side is the expected utility of W. Everyone believes me? Yes. So what we did is we said assume, I'm not saying everyone, but assume there is one decision maker that prefers X over Y. Then after some computations, we find that this decision maker has to prefer V over W. But that is a contradiction with our first observation, where we said actually everyone will prefer W over V. Right? So it means that if we believe that W should always be preferred over V, then anyone who prefers X over Y can never be in line with that observation. You cannot have a decision maker that prefers X over Y and W over V. It's not possible in the utility framework. Okay? Which is a problem, right? If we understand X, Y, if we understand W, V, we want to have a theory that has decision makers that prefer X over Y, W over V. And that's why we probably need a new theory that can explain this behavior, because expect utility theory cannot explain this behavior. Right? We need a new theory, which we call the dual theory, and that's actually a good exercise for you to try at the end of this chapter. The dual theory will help you to will be able to explain this behavior. All right. Does that mean that the dual theory is always better? Does that mean that, well, actually the expect utility theory was not so good, we have a better theory, let's throw away that other one? That's not the case. It's called a dual theory, meaning that there are things that cannot be explained in the expect utility theory that can be explained, that can be modeled in the dual theory. However, for any what we call a paradox in the expect utility theory, there is a dual paradox in the dual theory, meaning there are situations that cannot be explained, not be modeled with the dual theory, but that can be modeled with the expect utility theory. Right? So you can have similar but different examples as this one that give you a paradox in the distorted expectation, the dual theory, but that can be explained with the expect utility theory. Right? So we have two theories, and they are this. There's not that one is better than the other one. They are at the same level, right? They are equally good, so to say, but you have for every result that you have in one theory, you have a dual version of that result in the dual theory. Okay? So depending on your situation, you want to use expect utilities, you want to use distorted expectations. I think that's not a rule or a absolute truth that I'm saying here, but I think that as long as you talk about economical things, about behavior of investors, for example, you can use utility theory because the movements of your distributions are in what I explained in the beginning, this reasonable range, right, that we can understand. If you talk about extreme losses, risk management, then you better use a dual theory. Okay, this is what I just explained. Maybe let's take a short break before we go to the definition of the distortion functions and distorted expectations. So we take a short break, we continue back at 10. So we start with defining a distortion function. So what is a distortion function? A distortion function is a non-decreasing function g that goes from 0, 1 to 0, 1, meaning we start with the input of the function is a probability, and what comes out is, again, has to do with probabilities, right, from 0, 1 to 0, 1. And we need that the function starts in 0 and ends in 1. So it means that the distortion function is something like this. You start in 0, in 1 you end here in 1, and then you have a function, for example, that is concave, or you have a function that is convex, or some other function, right? It doesn't need to be always concave or convex, but it has to be non-decreasing from 0 all the way to 1. Okay, but convex and concave functions are important for our dual theory, like that convex concave functions for the expected utilities. Assume that we have a function that is, for example, concave, right, like the blue one. Then a function that is concave can never have a jump, right? Because if you, for example, take here, you want to make the function jump in this point, it will ruin your concavity, right? There is one exception. If you look at this function here, it starts in 0, then directly in 0, it jumps to this value, and then it's a concave function all the way to 1. This function g is concave and has a discontinuity in 0. It's not a continuous function. It's a function that is continuous on 0, 1, but has a jump in 0. Right? So it means that if you have concave functions, they can have jumps, but if they have jumps, they only can have jumps in 0. You can check if you do the same for 1, it doesn't work. A jump in 1 for a concave function will ruin your concavity, but it can jump in 0. For convex functions, it's the other way around. They can jump in 1, but not in 0. Right? And that's why we say convex and concave distortion functions are continuous on the open interval 0, 1, but they may have jumps in 0 or 1. Right? Okay. Oops. So how are we going to use these distortion functions? We are going to use the distortion function to distort, to stress probabilities, right? We want to increase the likelihood of having gains. We want to decrease the likelihood of having losses, right? We do a stress test on our actual situation of our loss random variable. So X is a loss, right? So it's a loss, meaning that we have a distribution, a CDF, for example. This is the CDF. Fx, then we know that here are the losses and here are the gains, right? If you talk about losses, then if you remember from chapter 2, then we are looking, for example, at this probability here. We look at the CDF, right? Here is X, here is Fx of X. Then we define F bar X as 1 minus the CDF, meaning it's this length here, which is the probability that you exceed the threshold X, right? We are looking at what is the likelihood that we get a loss X or even bigger, right? It's a upper tail probability. If we talk about stressing probabilities, we want to make this probability larger, right? Assume that you have a loss random variable X. On average, it has a loss of $100. You look at the CDF in 1,000. Then you take 1 minus CDF. That's a probability that your loss will exceed $1,000. You don't want that. And now we are going to stress that probability. Maybe in reality, that probability is 1 over 3. We will stress it to 2 over 3. We will make it larger, right? That's the idea. Okay. So it means that, whoops, we are looking at these tail probabilities, right? So P x larger than x, this is what we call the upper tail, whoa, tail, yeah, probability. And now we are going to stress that we apply a function g, that will be our function to stress the probability on this probability. Right? So assume that you are doing the modeling in your company, you are calculating how much capital does your company need to hold to cover losses in the next year, right? You have all your data analytics tool, all your risk measures, everything, solvency models, you put all your numbers in and a solvency margin comes out. Then the regulator tells you, well, can you repeat your whole analysis, all your calculations, but I'm giving you the function g. This is the function that I want you to use to stress your probabilities. Right? So I am the regulator, you're the modeler. I'm giving you the function g. That's the function that I tailored. I'm saying this is the function you will use. You did all your modeling. You determined your CDF and hence also your 1 minus CDF, this probability. And now you're going to apply the function g that I gave you on all these probabilities. So you have your tail probabilities. You have my function g. That results in what we call these distorted tail probabilities. And now you will continue calculating all your risk measures and solvency margins, not with the real probabilities, but with the distorted tail probabilities, and see what comes out. How much capital do you need in that stressed scenario? Right? That's what we're doing. Okay? So the function g is a distortion function. That's what is given. However, if you think about x as a loss random variable, then of course you want that these probabilities are larger than these ones, right? That would be a real stress. Otherwise, you make the situation better than in reality. If you think about the function g, you know that the function g is a function that has to start in 0 and has to go to 1. Then this function here is a distortion function, right? It's a linear function. It starts in 0, goes to 1, non-decreasing. It's a distortion function. Of course, if you use a linear distortion function, it means you are not distorting anything, right? It means that, well, you can apply this function g on these tail probabilities, but nothing will happen, right? Very boring. But what you can do is you can use a concave distortion function, because you have a concave function, but that concave function has to start in 0. Meaning it will always go something like this, meaning if you have a concave function, your, well, let me do it like here. Here is g. Your g of q will always be above the yellow line, which is the linear function. It will always be larger than q. Right? If you take a concave function that has to start in 0 and has to go to 1, in 0, 1, it will always be above that yellow line. There's no other possibility. So if we then use this function g to distort these tail probabilities, you easily find that this holds. That your distorted tail probabilities are larger than your real tail probabilities. If you use a convex function, it's the other way around, right? Then a convex function will be like this, and then GQ will always be below the yellow line. You will decrease your tail probabilities, right? And then we find that if we have a, well, if G is, well, if we have a loss random variable, then we better use G concave. Right? A loss random variable, we are distorting upper tails, and the upper tails are the losses. We want to increase these. If we have an income random variable, then in that upper tail, there are the gains. And if we are going to stress an income random variable, we need to decrease these probabilities. Right? We are saying, well, you think that the probability that your portfolio will get a return of 5% is 50%. We're saying, well, let's make that probability a bit lower. Right? Let's reduce that to 30% and see if you can, with that reduced likelihood of getting an average return, can you still survive for the next year? Right? We want to decrease the upper tail probability, so then we use a convex distortion function. Right? So we need both convexity and concavity because it depends whether we use with income random variables or we use loss random variables. Loss random variables, concave functions, concave distortion functions, income random variables, convex functions. Coming back over what I said in the beginning about these bid-ask prices, if you work in a financial context, you are mostly talking about income. You are looking at the payoff of your option. That's income. If you're going to distort that, you define convex functions, convex distortion functions. We in this course, we are talking about losses, risk management. We are looking at distortion functions. We define them on the concave levels. Right? So if you read the book on conic finance, I hope you will do, you will recognize the formulas, but you will see they are slightly different. Why is that? Because they express everything in terms of convex functions, because they work with income random variables, and we do everything in terms of concave functions. But you can easily, we will see later on, you can easily make the transition. Right? You have to translate a bit the two worlds. All right. I have here an example. You can do the calculations yourself. I think in the video you have all the detailed derivations and proofs and everything. So I'm not going to give that here. But what I do is, just to illustrate, I take a log normal random variable, right? After last week, we understand a bit how log normal random variables work. So we can, for example, calculate the tail probability of a log normal random variable in terms of the CDF, the distribution function of a standard normal distribution. In both in finance and in actuarial science, if we derive formulas, closed form formulas, what do we mean with closed form formulas? It means that we are looking for something, a tail probability, a call option, a stop loss premium. We want to have an expression that tells me the thing I'm looking for on one side is equal to some blah, 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 but what is in there are parameters, things that you can easily type in Excel, right? If you have the CDF of a normal distribution, it's not exactly closed form, right? It's an integral expression over that complicated density we saw in chapter 3, but we say even Excel can calculate probabilities of that normal random variables very accurately, right? And if Excel can do it, it must be very easy, right? So if we can derive a formula in terms of the CDF of normal distribution, we call that closed form. Think about your Black-Scholes option pricing formula, same thing. We call that closed form, although there is a normal CDF involved, right? That's what we do here. A closed form expression, at least something that you can easily plug in Excel to calculate all your tail probabilities, okay? Then we look at this distortion function, square root function, just very easy function. To distort, we have the tail functions, we have the distorted tail functions, right? So what you should do is you try to derive first these formulas, then you take your Excel, you take a first column with X values, you calculate your tail probabilities for different values of X, right? You have a log normal distribution, so you go from 0 to plus infinity. Then you calculate in column B all your tail probabilities with this formula 1. Then in formula C, you calculate all your distorted tail probabilities, and that you put in a plot, right? Excel, R, Python, MATLAB, whatever. I think for this type of things, Excel is actually quite good because it gives you all the intuition. Like if you code it, of course, you get more flexibility. But if you can do it in Excel, you can really see what is going on in your formulas. That's not a bad choice to take Excel. Anyway, if you do that, you get these two plots. You get the blue plot, this one. Well, let me do that in blue too. You get the blue plot, which is the tail function of x. Right? Again, you work in the company. X is the total loss of your company. That's all your income from investments, losses from life insurance, from annuities. You take all that data, you do some modeling, you get your loss distribution X. Right? That's the blue line. That tells you what is the probability that my loss will exceed a certain threshold, say 50. And say, well, this is a probability that we will get a loss which is more than 50, saying something, right? If you then look at the stressed probabilities, you have the red line is G f x of x. That's my stressed probability. You see, I push that blue line up, meaning I'm increasing these tail probabilities. The probability that you get a certain loss or bigger is becoming larger when I jump from the blue to the red line, meaning we are putting a stress on my probabilities, right? We're making the situation worse than it is in reality. Okay? Everyone still following so far? Yeah? Okay, an important observation to make here. If we look at the blue line, right, then, well, we know that f bar x, the tail function is 1 minus fx, right? The fx is the CDF, and of course, if you have a CDF, you have the tail function, right? There's a one-on-one relation between CDFs and tail functions. What was so important on the CDF? It's that the CDF characterizes the distribution, right? So we can define a distribution for any a distribution function for any random variable, right? So there are certain properties that we need for a CDF, right? A CDF, fx needs to start at 0, go to 1, and have right continuous jumps, right? We can translate that to the tail function, f bar. Of course, if f, the CDF, is increasing, the tail function 1 minus should be decreasing, right? That's fair. If you have a look at the blue line and the red line, then you see that actually they both represent tail functions of a certain random variable. Meaning that if you have a CDF or a valid tail function, you can pick what you prefer. You can always say, well, this is the random variable which corresponds with that distribution function. All right, so if you start thinking now, you are writing down a distribution function, right? You can pick any, but it has to be a valid distribution function going from 0 to 1, non-decreasing, right continuous. You map that to a tail function, 1 minus your function. Then you can think, okay, what is the random variable that is behind this distribution function? Right? You have a distribution function. There is always a random variable that corresponds with that distribution function. All right. If you look at the blue line, of course, that's a tail function 1 minus the blue line is a distribution function. There exists a random variable that gives you exactly that function. Of course, that's the random variable we start with is our log normal random variable. That's fine. But if we look at the red line, it has exactly the same properties as the blue line. It just is a bit larger, but it's starting in 1, decreasing to 0, continuous, so that's fine. So if you look at 1 minus the red line, what we find is again a CDF, is a function that qualifies, that satisfies all the properties a CDF should have. Meaning there exists a random variable y, there exists a random variable y such that if I calculate the CDF of y, I get 1 minus the red line. Do you agree with me? If you take 1 minus the red line, you look at your properties of a CDF, it satisfies all these properties. Of course, the underlying random variable is not x, because the distribution of x is the blue line, and a distribution only has a random variable, only has a single distribution. So it's a different distribution. But we can associate a new random variable y with that red line. So what does it mean? We go back to our example of the insurance company. You gathered all the data and you calculate the distribution of your future loss, right? Meaning that you found the random variable x, right? You can do two things. You can say, well, I derive the distribution function, and you also have the random variable x that represent the future loss. And then you can say, well, let's have a look at the expected loss, the variance of the loss, the value at risk of the loss, the skewness, the whatever measure you want of your random variable x. Then what I said before is, if I'm the regulator, I give you the function g. I say, well, can you please stress for me your tail probabilities? What I could have also done is I could say, well, can you please for me change your random variable x into this random variable y? We replace the x, the reality, with my stressed scenario, which is y, which in this case will be equivalent. Either you stress the tail probabilities with g, or you replace the random variable x with y, right? And I hope that you see that these are things that exist on different levels. Either you work on the level of the random variables, x is replaced by y, or you work on the level of the distribution function and the tail functions. You go from the tail function of x to the stressed red tail function, which is, and that's your link, is the CDF of your red random variable y. Right? So you see that in this case, you can pick one of these two. Either you work with the random variables, x going to y, or you go from the tail function x to the distorted tail function y. Y. Okay. The problem is, and that's discussed in detail in the course notes, is that from the moment you have jumps, this whole idea of saying I distort the tail probabilities or I change the random variable x with a new random variable y, that becomes a bit complicated. If you have jumps, it can happen that your red function has left continuous jumps. Or 1 minus the red function, the CDF has left continuous jumps. Which means it's not a CDF anymore, right? And that makes the translation from CDFs to random variables a bit more complicated. I put a note on Toledo, where you can derive the conditions such that you can, what I just explained, can actually do that with any distortion function. What are the conditions on the distortion function such that you can always say either I distort the tail probabilities, or I replace the random variable x with a new random variable y, that these are equivalent. If your distortion function is continuous, like in our case, everything is fine. The condition, you can relax that continuity a bit to left continuity, right? And that's explained in the note on Toledo. So please have a look at that note, and there you find the details how we can go from distortion function, distort expectations, and this y random variable. All right. Okay. Then the definition of the distorted expectation. So if we have the distortion function g, then my distorted expectation of x is this rho g of x, and is given by this expression. We assume here that both integrals are finite. Why is that? Because if you have plus infinity in both cases, you have plus infinity minus plus infinity, that's a problem. If you want to relax that assumption that both integrals has to be finite, you want to relax it a little bit, you can assume that at least one is finite, right? Because if at least one has to be finite, it means that your distorted expectation can be either minus infinity or plus infinity, right? That's fine. But we want to stay in the finite case. We assume that both integrals are finite, meaning that my distorted expectation is always finite. Okay? We call rho g of x this thing here. This is in R, right? We call this the distorted expectation. And the function rho g, the function rho g that attaches to each random variable x a number rho g of x which corresponds with the distorted expectation, that function is what we call the distortion risk measure. So we have the function that is the risk measure. We have the quantity, the real valued number, that's the distorted expectation. Okay. Let's have a look where this distorted expectation comes from. If you remember, with the stochastic dominance, we had this formula. Actually, we had the formula, well, maybe I'll write it down here that you recognize it. The formula we had for the expectation was minus an integral first over the CDF, and then an integral from 0 to plus infinity over 1 minus the CDF. But the CDF is equal to 1 minus the tail function, and 1 minus CDF is equal to the tail function. All right, so then you find this expression here for the expectation. Okay? So what we do with the distorted expectation, we say, well, let's have a look at these tail probabilities, and instead of in that integral throwing in your real tail probabilities, we first are going to stress these probabilities with the function g. So we change the probabilities with the function g, and then we plug them in the same formula. Yeah, so assume that you wrote some piece of code to calculate the expectation of x using this formula. Then you first calculate the tail function of x, then you calculate the two integrals and you put them together. Then in order to do the distorted expectation, instead of putting in the real tail probabilities, you plug in another vector with distorted tail probabilities. So it's basically the same function you are using, but you give a different input, right? And that's what we call the distorted expectation. So assume that I define the function f, y, x, well, no, let me call it g. I define the function gx as 1 minus g fx of x, right? Assume that I define the function g in that case, in that way. Assume that g is a valid CDF, right? Meaning that g is a right continuous function going from 0 to 1 in a non-decreasing way. Then, so if I assume that, then I know that there is a random variable y such that the probability that y is small equal than x is equal to g of x, right? Maybe I should write this in a slightly different way. No. I write this as then there exists a random variable y such that this probability is equal to g of x. You all understand what I'm doing here? Linking the CDF, the distorted CDF, with a random variable. But then this here becomes minus the integral from minus infinity to 0. 1 minus g was equal to the function gx dx plus 0 plus infinity, we have 1 minus the function gx dx. But if we are in this situation, then gx is a CDF of y. We use this expression here, but then for the random variable y, we find that this is equal to the expectation of y. That random variable that has CDF equal to g. Right? Again, what is important is that we find that rho g of x is equal to the expectation of y. There exists a random variable y such that your distorted expectation of the random variable x, your stressed expectation, is like a regular expectation, but for a new random variable. Right? So if I'm looking at the distorted expectation, then we are stressing the tail function. So I'm telling you, here you have a function g. Can you apply that function g on your tail function and then calculate all your expected losses? Or you can use the right-hand side where you stress the random variable. So in that case, I'm telling you, I'm not going to give you a function g. I'm telling you, well, can you replace your loss random variable with my random variable y? And do all the calculations on y instead of x. Okay? If this holds, then these two approaches are equivalent. It will give you the same results. Okay? Why is this important? Because if we can derive that random variable y, we can maybe understand better what is that distorted expectation actually doing. Right? If you understand how y is different from x, then you can see, well, how am I doing my stress? And is that what I want? I can just give you a random variable, a function g. I can give you something. You can put all the numbers in there and see what comes out, but we also want to understand why do we get what we get. right? If we can track down that y, we compare the random variable y with the random variable x, maybe that can help us to understand, right? And in the notes that is on Toledo, and I think also in the exercises that I will post this week, there will be several exercises where I give you a function g, a distortion function. You have to derive that random variable y or the other way around. Then you will see that for, if you choose the function g in a good way, if you choose the random variable y in a good way, you can derive distortion functions and distort expectations that actually make sense, that you can understand, right? You can understand, what am I doing with this distortion function, all right? That's why it is important to understand this. Okay, so the condition that you need such that this here holds is that we have a function g that is left continuous. Yeah, that will be the condition that will make sure that this works. And that, again, in the note on Toledo, you can find a detailed proof of that. Okay, clear for everyone? Questions? Then if you have questions, please ask me. Here's the chat. No questions, I see. Let me have a look at the graphical interpretation. So we had this expression for the expectation of x, right? Which gives you an interpretation of the expected value of x in terms of two surfaces, right? Where in the stochastic dominance, we were drawing these plots using the CDF, right? We can do the same, but then using this formula here, meaning we draw the tail function, right? And that's what you see here, the dotted line or the dashed line here, which I go in blue, that's your tail function, right? And because we take an integral, so for the expectation of x, my integral is on 1 minus the tail function on the negative side and the tail function on the positive side, I get the area below the tail function, which is here, 1. So I get the surface 1. I have to subtract 1 minus the tail function from minus infinity to 0, meaning it's all this surface here, which is in my, with the numbers, 2 plus 2 prime. If I'm now going to distort that tail function with a concave function g, concave function g means that I will increase the tail probabilities, right? I will go from the blue line to this red line, for example. Right? That's my distorted tail function. If I push that up, you see that on the positive side, from 0 to plus infinity, I add this part to the surface. Right? So I'm not having only 1, I have 1 plus 1 prime for my distorted expectation. Right? What do I subtract? I subtract now because I push my function up. On the negative side, the area in between your tail function and 1 is getting squeezed, it's getting smaller. Right? Instead of having 2 and 2 prime, now I'm only having this 2. Right? So I increase the surface on my positive side. I decrease the surface that I will subtract on the negative side, which means that your distorted expectation will be bigger than your regular expectation, right? That's how, if you try to visually have a look at what's going on, that's what's going on. You push your tail function up, mean you increase the surface on the positive side, you decrease the surface on the negative side, okay? I already introduced the very simple distortion function, the linear function. Then, of course, nothing happens, and your distorted expectation is equal to the expectation. That's your linear function. Then we have that concave functions will result in an increase. Your distorted expectation is larger than your regular expectation. Convex functions, because you are below the linear function, will decrease your expectation. Which also shows you that you want to use concave functions if you have loss random variables. You want to use convex functions if you have income random variables. All right? Then we have here three properties on distorted expectations. Remember that for an regular expectation, you have that the expectation of A times X is equal to A times the expectation of X, right? And this holds for all A. And we have that the expectation X plus B is equal to the expectation of X plus B, right? Then we can prove that these results also hold for distorted expectation, but now A has to be positive, right? If A is positive, then you put the A inside and you can put it outside. It is a kind of linearity that you have there. And you can translate, you can move your random variable X to X plus B. You just add it at the end, right? So that's similar to what you have with expectations, except that your A has to be positive. Only positive transformations work. All right. For the proof, I think it's a good exercise to try to prove this yourself. How do you prove that? You start from the definition of a distorted expectation using the tail function, but not the tail function of X, but the tail function of AX. And then you rewrite that expression to a tail function of X. All right. Same for 2. All right, so I think it's a good exercise for you to try. Again, if you have problems, then please contact me. I can help you if that is necessary. But I think it's a good test to see if you can play with any distorted expectations and the distribution functions. Right? There's nothing. I think you can best start with property 1. That's the easiest one. Property 2. If you did property 1, you will need the same approach for property 2. It's slightly different. They're slightly more difficult. Well, you will find out that there is something you have to take care of. Okay? And then the last one, I hope that is how do you say that is trivial, because we define everything on the level of tail function CDF. So if these CDFs are ordered, you stress the tail function. So 1 minus CDF with the same function G, you automatically get an ordering of your distorted expectations, right? I would think there are no surprises in that. Okay. Another important result is the following. So assume that we have a function G that jumps, right? We have the function G that, for example, this function from 0 to 1, and you have 1 minus p here, and the function is, the distortion function is 0 all the way until you are in 1 minus p, and in 1 minus p, it jumps to 1. It's this function, right? It's a jump function where you have a right continuous jump in 1 minus p, right? If you have this function, then again, you try the calculation yourself to see that the distorted expectation is equal to this plus inverse. You prove it by just starting from the definition of a distorted expectation, right? You start with the definition of a distorted expectation, Then you use this special distortion function, you calculate, and you will find, I hope, this result. Again, if there is something that doesn't work, then please ask me. Okay, the point that I want to make here is that if we now change that function a little bit, and we go from a right continuous jump to a left continuous jump. So I keep the same function here. I only change the function value in 1 minus p. Instead of having function value in 1 minus p equal to 1, it's now 0. So my distortion function remains the same, except that in 1 minus p I do not have a right continuous jump, I have a left continuous jump. Then what you get, again, you try to do the derivations, you get that your distorted expectation is changing to not the plus inverse, it's changing to the normal inverse. And if you remember the start of chapter 3, we talked about these inverses, and I showed you that the plus inverse is different than the regular inverse. If you have horizontal parts of your CDF, this one is different from this one. So what is important to see is that if you have a distortion function, if you have a distortion function that has jumps, then right continuous jump, left continuous jumps, they matter. Right? They will change your formulas. And that's why in the course text, you will see that we spend a lot of time on deriving formulas for distortion functions with only right continuous jumps. Then we consider distortion functions that only have left continuous jumps. And then we merge the two results to discuss distortion functions that can have right continuous and left continuous jumps. Right? I'm not going because it's rather mathematical, all the what we are trying to derive there, but on a practical level, it is important. Because if you just switch from right continuous to left continuous jumps, your distorted expectation will change. And if you use it as a risk measure, your risk measure will change, right? So that's why we spend some time in the book to discuss the type of the jumps. Okay. So I already explained you that we both need concave and convex functions when we are talking about losses and gains, right? If we have losses, we want to talk about concave function. If we have gains, we want to talk about convex functions. And for example, what we are doing here is mostly we work with loss random variables, meaning that we will look for good concave distortion functions. And if you do that bid-ask pricing, conic finance, you're working with income random variables, you need convex functions. What we need then is if we have a good concave distortion function, then we want to use the same distortion function, but we want to use its convex counterparts that we can use on income random variables, right? So we want to have a natural way to move from the concave distortion functions to the convex distortion function and vice versa, right? And that's why we define this dual distortion function G bar, right? So if we have a distortion function G, right, your favorite distortion function, then you can define G bar in this way. It's 1 minus the function G in 1 minus Q. What you have to prove first, and I hope that will be an easy exercise, you have to prove that this is again a distortion function, right? It satisfies all the requirements of a distortion function. Starting 0, goes to 1, is non-decreasing. Easy to prove. What you can also prove is that if your function G is right continuous, then G bar is left continuous. Why is that? Because you have the 1 minus Q here, right? If your Q goes from 0 to 1, the 1 minus Q goes from 1 to 0, right? So approaching a jump from the left becomes approaching a jump from the right, right? That's why right continuity becomes left continuity and left continuity becomes right continuity. We also have that if G is convex, then that dual distortion function is concave and the other way around. Again, you can prove this very similar as we did with the utility functions, right? We had convex utility functions, and then we defined that function v, showing that this is a concave utility function. Something similar holds for the distortion function. Again, you try that yourself. What is important is that now we have a natural way to go from a distortion function that is good for losses, concave, to a distortion function that is good for gains, right? So if you have your favorite distortion function to model losses, if you want to apply it for gains, you just go to the dual distortion function. If you read a book on conic finance that deals with convex distortion function, you say, well, if I want to apply it on my loss random variable, I just swap to the dual distortion function, right? And you will see that in that book on conic finance, what they call the formulas that they have and where they use the distortion function, actually they are the same formulas that we have here, where you have to change the distortion function to the dual distortion function, right? Because we have to go from the situation where you have income to a situation where you have losses, right? So that's a bit the difference that you have between the conic finance and the risk measures, okay? But important is to see that the dual distortion function is a natural way to go from distortion function for losses to distortion functions for gains, okay? And here I use the same example as I had in the beginning with that log normal random variable. So the blue one is the CDF of X. The red one is I distort my CDF with the concave function G. And the green one is the one where I distort not with the function G, but with the dual distortion function G bar. And then you see that if you have a concave function G, then going from the blue line, I'm pushing my probabilities up. I go from blue to red. If I distort with G bar, I'm pushing my probabilities down, right? So what you have is that if I like this function G, then I know, well, if your X is given by the blue line, if you tell me that X is a loss random variable, I say, well, use the stress probabilities in the red curve. If you tell me X is actually an income random variable, what I receive, and I say, well, then you have to use the stress probabilities which are on the green line, right? So it depends what you call stressed. It depends on whether you have an income or a loss random variable, right? But with that distortion function and with the dual distortion function, you can use both, right? If you have the distortion function, the dual distortion function, then you say, well, tell me if you have a loss or an income random variable, and I will tell you how to distort, right? That's what the dual distortion function is doing. Okay, you can, it's a good exercise to use this function GQ that we had before, right? With the jump, and then determine the dual distortion function and the distorted expectation using the dual distortion function, right? Because we have a distortion function G. I can use a distortion function to determine the distorted expectation of X. But because I also have a dual distortion function, I can apply that dual distortion function to calculate the distorted expectation, and then you get this one here, right? So for this simple distortion function, you can try to derive that dual distortion function, all right? Again, for everything that I tell you to do, if you have problems, please let me know, right? I think even if you can get started with the exercise and you are stuck at some point, I can help you a bit. I think you will learn more with that than when I just give you directly the results, right? Okay. Interesting property then, theorem, is that you can link the dual distortion function with the dual distortion function and the dual distort expectation with your regular distorted expectation. For example, if you look at the distorted expectation of x where I use the dual distortion function, it means that, for example, if g is your distortion function for a loss random variable, but x is an income random variable. So then I say, well, if I need to stress my x, I first need to go from the distortion function g to the dual distortion function. And then I calculate my dual distort expectation, right? Then what you can also do is say, well, instead of changing the distortion function, you can say, well, if x is an income random variable and g is a distortion function for losses, let's switch from x to minus x. Because if x is a income random variable, minus x is a loss random variable, and I can use my function g and my distortion function with the function g. I can use that on minus x. That's what you do here. So you calculate your distorted expectation on the loss random variable minus x, and then you apply again a minus 1 because you express everything in terms of losses and you have to translate it back to gains. Right? You see what's going on? On the left-hand side, this one, you change your distortion function such that you can directly use the dual distortion function on your income random variable. On the right-hand side, you change the random variable from x to minus x, from a loss to an income random variable. Then you apply your function g, and then at the end you translate back from rho g to minus rho g, because you have to go from loss to income again. Everyone is following that? Some of you look confused. No? Okay. What is interesting is that if you take an expectation, assume that x is my income, right? I look at an income and I look at the expected income that I get. I can say, well, let's go from my income x to minus x. Take the expectation of minus x, meaning it's my expected loss, right? If I have an income random variable that is on average 100, right? On average, you will receive 100. Then I go to minus x. Your average will be minus 100, right? And then you say, well, let's move back to your income setting by again applying the minus. For expectations, of course, you find that this minus and this minus will cancel each other, right? That basically you can put this minus inside so that you have minus 1 times minus 1. For distorted expectation, that doesn't work, right? You cannot bring this minus inside your distorted expectation. Why is that? Because if you remember this property, it doesn't work, this one, it doesn't work with minus 1, a equal to minus 1. A has to be positive. If you take negative values, minus 1 for example, you cannot bring it inside and outside your distorted expectation, right? And you get this formula here, right? You first have to change the random variable, then apply the expectation, and then swap back again, right? Whereas with expectations, you find that this, of course, is equal to the expectation of x. Okay. Is this clear or maybe not? To prove this expression, again, I put it here as an exercise. I think it's good to try it yourself. And let me know if you found out that there are some problems. But I think it's, again, it starts, all these exercises are the same. It starts from the definition of a distorted expectation, and then you just plug in whatever you need, right? In this case, you start from the definition of a distorted expectation with G bar, and then you rework it to the function G, right? It's always the same what you apply there, right? So I think it's good to try it yourself. Okay, I think I will end here. What we do in the last part of this chapter is to again relate these distorted expectations with decision making under risk. Right? Again, we say, well, assume that you have X, you have Y. How are we going to use distorted expectations to decide which one is better, X or Y? Right? I have no time to explain that in detail here in the lecture, but you have the videos, and in the last part of the videos you find all these detailed explanations. So please watch the videos to get all the details on that part. It's the same with chapter 3. There also we skipped the last part on correlations and rank correlations. Again, it's explained in the videos, so please watch these videos because it is part of the exam. Right? So assume that you watch the videos, you study the videos, you ask questions if something is not clear. All right. I think I will end here. I will be available after lectures. If I was going too fast, if there's something you do not understand, please ask me. I'm happy to explain some things that we covered here that were unclear to you, or other parts of the lecture, previous lectures, right? So if something is not clear, please ask me. I'm happy to explain things again, or to help you with exercise you tried, to like these exercises I gave you in class. I assume that you do them, and if there are problems, that you come to me. Right? So if I do not get any questions, I assume that you managed to solve these exercises. Well, so never hesitate to ask any questions. Last thing I want to say is that I think I told you that on the exam, I hope that you can write and organize your solution in a decent way. The other thing is that for questions, I will be available in the Christmas holiday, in the study period in January. So please, if you have questions, then please send them to me. Of course, say 1 week before the exam, if I get many questions, it can be that it takes longer to answer your questions. And if you send questions one day, 1 hour before the exam starts, that might be problematic to answer your questions on time. So if you have questions, if you know them already, then it's better to ask them on time, because sometimes it's very busy right before the exam. There's one question here: how long is the exam? The exam is current setup is, I think, 3 hours. It's 3 or 4 hours. I'm not sure, actually. Let me check that. So the exam is designed for 3 hours. It could be that they give you in the exam schedule that they give you 4 hours. Well, then it's 4 hours. But the sample exams that I post on Toledo, they are for 3 hours. Okay. but I don't know how they schedule the exam in the exam schedule. Maybe it's 4 hours. If it is an online exam, I think it's only 2 hours. So if there is an online exam, I think, at least that's my experience, then it's limited to 2 hours. So that's why I said in the beginning, then the exam will slightly change because I need a little bit different type of questions, less questions, different type of questions, so that it covers all the material, not in 3, but in 2 hours. Okay, did that answer your question? Maybe not really. It can be 2, 3, or 4, basically. Okay, other questions? If not, but yeah, for the exam, keep an eye. Keep an eye on Toledo, on the official channels of the faculty to see what is going on. So for the moment, again, it is as it is described on Toledo, unless we change. Okay, if there are no more questions, then I thank you for your attention, and I hope that I will see you back next week.